Okay, in the last example, we will build the particle filter for DC motor system. Okay, so we need to define the parameters in here. J is 0.01 and C is equals to 0.1, KV is equals to 0.01, delta T is equals to 0.1. This is the second. Okay, and Q is 1 e minus 5, R is 1 e minus 3, and UK is equals to the 5, for example 5 PWM rate, and so T 50, and N, as always we do, the number of particles, and also this is the number of time steps. Okay. In this case, allocate the arrays for the x true value, zeros to t, okay, and y, zeros 1 t. This is the observation or the measurement coming from the sensor. This is the true state, desired state. Okay, and so first of all we initialize the true states in here. X true 1, 0 and 0. Okay, after that we need to define the VK or process and measurement noises. VK sqrt q times rand n 1t. Okay, this is the process noise, and wk is equals to sqrt r times rand n 1t. This is the measurement noise. Okay. So first of all we need to generate the true state and observation for k equals to up to t, and x1 is x true 1 k minus 1, x2 is equals to x true 1 k minus 1, but this is 2 because it's the velocity, and x true 1 k is equalized with the x1 plus x2 times delta t. Okay, this is the backward Euler representation, and x true 2k, just like in the PowerPoint writtens, x2 plus times delta t plus vkk. Okay, and so we need to fill the inside c divided by j times x2 plus kv divided by j times uk. Okay, so these are the what are states, and so yk is equalized with what the x true 2k plus vkk wkk or this is the velocity. Okay, we measure the velocity values here. After that, just like remember the previous example, particle filter initialization can be done with the particles is equals to the zeros 2 and t. In that case we have two states, and so 2 times n particle numbers and the t time steps, and so we have 3 dimension in here, and the weights is equals to the zeros and t, and particles initialize with the total elements and 1. This is the first time step, and so the zeros 1 and zeros 1 n. Okay, because we have to what, to 0 conditions, or we can assign the rand function. We can use the rand function, but we know that the initial condition of these values are equal to what, to 0, and so this particle at the prior level must be equal to the what, to the 0. Okay, this is the prior knowledge. So also we need to initialize the weights with the what, the total elements of these terms, 2 states, and 1 must be equalized with the what, the ones, and 1 divided by n. Okay, this is our representation. This is the first weight for the 2 seconds. And so if we are using the n is equals to 1000, and so we have the weights 1000 times 1 in here. We have 1000 weight in here. So how we can apply the particle filter algorithm? For k is equals to 2 to t, okay? And so in the prediction we should use the what, the nonlinear or linear system. x1 pre-values the particles 1, total elements k minus 1, okay, and x2 prev is equals to the particles second state whole elements and k minus 1, okay, and vk particles must be equals to what, the sqrt q times rand n 1 n. This rand n function generates different from the what, from this one, okay, this is important. So after that x1 pred must be equalized to x1 pre value, the prediction values, plus x2 previous value times delta t, okay, and x2 pred is equals to the x2 pre value plus just in case in simple form we can write to the what, to this equation in here. This is the same because cj, but this is the x previous value, this is the uk, and also we need to give the what, the vk particles at each time. And so for at each step we will drive to the what, the 1 times n random number to what, to generate the different samples in here, just like this one, okay. And so the particles first elements or the position can be assigned with this one, x1 pred, and particles to whole particle elements k value is assigned x2 pred, okay. So the update must be done with the yk is equals to yk, okay. And so after that we need to compute the likelihood manually, okay. Residual is equals to the what, yk minus x2 pred, okay. Because x2 pred is our desired prediction values in here, but the yk is the measurement, and so yk always possess the what, to our noisy signals. It's coming from the sensor, it contains the noisy signals, and x2 pred also contains noisy signal but at the different form of these terms, okay. And so we want to build the likelihood in here just like this one. Just see, exponential term minus residual dot over 2, okay, divide by, just remember the 2 times r, and divide by sqrt 2 times pi times r. These are the general formulation for the what, the likelihood calculation. And after that the rest of them is simple. Just see the update of the weights, update weights can be done with the what, with the previous algorithm. Actually this is the same. I can copy off the whole of these things in here, because rest of them is the same. And comments, and so I can just look at the what vk, I'm sorry, this to normalize files, and the weights, total value k is equals to the what, the weights total value k minus 1 dot times likelihood transpose. Okay. After that we normalize the whole weights in here, and the effective sampling must be done, and cumulative sum weights calculated, recalculated, and cumulative sum in here j. But now we need to give the what, the two states in here in this time, and so this particle must be given this time, just like this one. But we have the weights in here, whole elements k value once and divided by n. Okay, this is true right now. Okay, but the only difference is that we have two states in here, unlike the previous one. Okay, and so if I run this code, I can check there's no error. Okay. And after that, for the state estimation, we need to give the xs values, the zeros to state for t time step, and for k is equals to the 1 up to t. Okay, and xs k, the particles dot total state, total particles, and the k elements times weight times k. Okay, that's all. This is the estimation value. First of all, we need to give the figure and the subplot 2 1 1. Okay, and so the plot 1 to t x through first position value k minus, and line white. Okay, and so 2 and hold on must be given in here, and we need to copy all of these terms in here. K is the red, but in this time x estimation must be given in here, and also we need to give to what, to blue line, or the estimation is the red one, this is the blue line, and this is the y. Okay, so these are the signals representation, and so x label is the what, the time step, and y label is equals to the what, the angular position, and legend must be given in here is the true state or true position in terms of this one, and so estimated position and measured position coming from the or sensor position, which is given in here, and grid off. Okay, after that we can write the same condition for the velocity value is a 2, but the y is obtained what, yk is only contains to the what, this one. Okay, and so first of all we cannot write this one, but this value can be given in here with the velocity value, because we have only one sensor to what, to get the whole the values of the velocity in a real-time application. Okay, xs true, x true, and y. Okay, so if I run this code, just see that first of all the true position and the estimate position are on the same page. See, we have one difference in here. small differences in here. Okay, xs, x2, xs. Okay, but just see the second graph in here. But we can increase the values of these terms. The t. Yes, it's not necessary. Okay. So, see, we have estimated positions in here, just like this one. And so, it's not going to this one. And so, this one. And blue line. Okay. So, if I rerun this code, and then we will have to what? First of all, the x positions in here, just like this one. See, the position estimated and the true is close enough. But in the second case, see that we have true velocity with the noisy signals, and the sensor velocity is a noise signals. But the estimated velocity is going to do what? The straight line in here. This is a good performance for the what? For the angular velocity values in here. But if I choose to increase the values of the what? The SQRT values in here, first of all, 2 and 1 can be added in here, and this is too much noise in here, just like this one. And so the true position and the estimated position are closing enough, but not completely. But just see that true velocity is given in here in the dot black line, but the sensor velocity is highly noisy signal in here. But just see that the true velocity or estimated value is the best value in here. If I increase the what, the number of particles, just like the 10,000s in here, just see, in the 10,000s we have the best solution at the what, the estimated velocity value, and also have the what, the position value. And so if I increase the n value in here, and then we will have the best performance, but it's a time consuming. In the real life application or real-time application, for example, if you want to use the what, the STM or TI chip in the real-time system, we may have the many time to calculate these positions. Okay, but if I choose the small to this value up to what, up to 10, just see that this is highly stable solution in here. See, we have also a stable solution, just like this one. Or we can decrease the values of these terms in here. And so, just see, our estimation is going to what? Going to worst, but still it's good in the RMS value. And so the position cannot be predicted easily in here. But the direction of the position and the direction of the estimated position is going what? Is going into the parallel in here. But if I choose to increase the 1000 particles in here, and so to see that in the 1000 particles we may have the some observed conditions. And so if I choose the 10,000s in here, just like this one, see, our velocity value is highly enough to what? To predict or generate the what? The estimated velocity. More stable than the previous one. Okay? But this is the absurd case for this algorithm. Okay? For example, if we want to increase the delta seconds in here, and also we can apply the 100 time step points in here. To see, in this case, we will have the good results in here. The velocity value is more straight than the what, the blue line, and also true velocity value. This is good in here. And also we can take the n is equals to 10 times, and so just see that our position values, true position and estimated position, have the small error values, but just see that the red line, estimated velocity, is the more straight line, and the RMS value error between what the true velocity is smaller than the what the sensor velocity. This highly efficient technique to the what, to state estimation based on what the likely competition and the weights. This is more important because if we have the nonlinear system, and we can obtain to the what the posterior probability values based on this system dynamic equation just given in here. Okay.